Okay, let's start. A quick recap from the last class. So we saw, right, uh, an abstract form of convex optimization, which says that uh, a problem is convex if you are minimizing a convex function over a convex set. Okay, then we also say so. What is a standard form of convex optimization? Why? Because we will be sticking to this definition uh, throughout this course, and this is very helpful in many scenarios. Even many solvers are expecting problems in this form. Okay, so we saw how can we define a convex optimization problem. It should be minimization of an objective function, which of course has to be convex, subject to um, inequalities and equalities, but inequalities has to be this function which defines inequality has to be uh, they are convex. Okay, and then equality, for equality we should only use this form, that is it has to be affine function. If you consider an equality like this 0, then hi has to be affine. That's a criteria. So again, I want to revisit one of our discussion because there is one correction which is very important. That's why I am revisiting. So let's consider some cases and examine the convexity. So case one. So I'm saying that we have an optimization problem, and one of the constraint is S score is less than or equal to, for example, 4. Okay. So if this constraint is part of our optimization problem, then the problem is convex or not? That's the question. So only thing what you need to do is just compare this with the standard form, right? And see whether it satisfy the criteria that we established, right? So which is this term? This is inequality term. So we have to see here, right? And now what is the criteria? Okay, inequality has to be to this side. So that is okay. And yeah, 0 is okay. We can bring 4 to left side. That's okay. And yeah, so then only okay, maybe we can write, if you want to strictly stick to that, this is like x square minus 4 is less than or equal to 0. Okay, and now only thing is whether this function is convex or not. So this is convex or not. So what is it convex? Yeah, one thing is you can like think about the set, but this is a simple case. That's why you are able to think. Otherwise, you have to examine the convexity of this. In this case, this is a differentiable, twice differentiable function. So what you have to do is differentiate twice and see the whether that is greater than or equal to 0. Or if this is a vector, we have to check whether the Hessian associated with the that vector is positive semi-independent or not, right? So here, of course, this is like a function of this form, and this is convex. Or in other word, we can also examine what is the set corresponding to this inequality. This implies that x is between -2 and 2, right? So we have the line here, real line, and x is in this region, -2 to 2. So this is a convex set. So this problem is convex. Now, next case 2. This is very important. That's why I'm revisiting this. Yeah, this is the inequality. So what you have to do? Yeah, so make this in a similar form like this, right? So for that, what, so this is equal to minus x square uh, less than or equal to minus 4, right? I can bring this side first for which is less than or equal to 0. Is this convex? Yes, this is not convex, right? It's a convex. So because if you differentiate twice this guy, you'll get a negative number. Okay. Or in other words, if you examine the set, it will be minus 2. It will be this region, right? Which is not a convex set, because if you pick any 2 points here, here, then the line segment between that point is not the part of the set. Now, yeah, I'm just taking an example, make you go through a scenario where if these constraints are given, what happens? Let's assume that all other criteria are satisfied here. Okay, you have a nice objective function which is convex. Let's assume that you have an equality in an affine form. Assume that. Now, what happens if you have this? That's my question. Okay, right. Now, case 3. This is the place where we made a very stupid mistake last time. What was that? Yeah, x square greater than or equal to 0. This was the example. Okay, so what's your uh, uh, opinion on this? So again, if you are just blindly checking this with this, right? What will happen? This will be minus x square less than or equal to 0, right? So then, uh, is this a convex function minus x square? No, right? So then our problem seems to be not convex, right? But be careful. We saw last time, right? We should not be very blind on checking this, right? Sometimes this can imply a convex set, right? Here, see, what is this? Well, square of a number is greater than or equal to 0. So what is that set? If you take any number, the square will be greater than or equal to 0, right? Even if it is negative, positive. So that is the entire line. That is a convex function. So though if you check with the standard form, this seems like a non-convex thing, but you should not be very blind on that. You have to think a little bit, and this is a convex problem, okay? Because the set is a convex set. So in fact, when your problem, when you have this constraint, what you can do is just drop the constraint. You can remove the constraint because that will be satisfied for any x. So you can drop the constraint. So the problem in the original form is not convex. Uh, if you compare with the standard form, but you can drop that inequality and now say that you have an equivalent problem. This is equivalent problem. You just drop the inequality, and then that is a convex problem. So that's the idea of equivalent problem. But here, for example, you had this. Now to mm, make this compatible with this, you just brought the minus 4 to this side, right? But that's not that is a same problem. You are not changing anything, just bringing 4 from right to left. So that is the same problem or identical problem. But here you are dropping this inequality. Then you will be you'll be having is a, it's a different problem, but it's an equivalent problem which gives you the same solution, right? That's the definition of equivalent problem, right? Yeah, so that's the idea. Again, if you consider case 4, so x square is greater than or equal to minus 5. So let's write our conclusion. This was convex. This is not convex. This is convex. What will be this? Non-convex. Why? Okay. Okay. Let's. You just need to think what it is.
It is the same as the previous case 3. It's
Yes.
just always going to be positive. So it's just the entire real number line.
So yeah, correct. So like if you are blindly following the standard form, then you will be in trouble, right? So what was that? Minus x. This will be minus 5 less than or equal to 0, right? So it seems like a non-convex function, but you can drop this inequality because for all values of x, it will be satisfied. What you are saying is that square of a number is greater than minus 5. It will be satisfied, of course, right? For any number. So the set associated with this inequality again will be in the real line. Okay, so you have to be careful. Just don't be blind on that. Think about it. Okay, what is the set corresponding to that? Fine. So I want to make this very clear. Got it right. So I think there was a mistake in our discussion, some of our discussion regarding this part in the last lecture. So now it's clear, I hope. Okay, any doubt? Just take a few seconds because this is important.
So is there a formal way to check it then? Like with the mathematical step, like here we just sort of inspect it and see that it is convex because it is the entire real number line. But
yeah, so for example, let's take an example from last class. Which was that? Yeah. So what my point is, you should keep in mind, you should have an idea about the set in formed by the inequality. So here, yeah, this thing. So we had this, so which is not convex in the standard form because you have a square term as in the equality, right? But then you cannot say this is convex. Okay, in this form, sorry, you cannot say this is not convex. Of course, in this form, it looks like convex, okay? But you can come up with an equivalent problem, which is convex. So you can, this problem is non-convex, of course, in this form, okay? So what I'm saying is, just examine this, what is it saying? It's saying square equal to 0. It can happen only if this quantity equal to 0. That means x1 equal to x1 plus x2 equal to 0. Okay. So yeah, so the if you get a problem like this, or if you come up with a non-convex problem and your constraint seems to be non-convex, then you should not quit immediately. Just examine carefully whether you can link that to a convex alternative. Yes. So, but like in the case for you know, like, yeah. So that's why if you strictly want to say something with respect to your conclusion with respect to the standard form, this is not convex with respect to standard form. I agree. Standard form, this is not convex, but it's just the sake of defining things, right? So you can say that, okay, according to my standard form, this is not convex, but like I can make this convex. I mean, I have a problem case 4. Okay. Yeah. Just a second. Yes, case 4.
Yeah, here minus x square minus y, it's a concave set, right? Concave constraint.
Yes.
So
So, but what I'm saying is that is concave, but this is satisfied for this function is concave, okay? But the set formed by that function is a convex set.
but this is the constraint function to be convex.
Yeah, that's what I'm saying. If you want to make a judgment uh, by comparing with the strict standard form, you can say this. Okay, this is not convex with respect to my definition of the standard form. Okay.
We were discussing the standard form, right?
Yes. So what I'm saying is, okay, I agree. This is not convex with if you strictly want to make a judgment or statement with respect to standard form, this is not convex. But the thing is, uh, the point that we have to go through is this: why do we come up with a standard form? That was not our original definition of convexity. What was the original definition? It was like you are minimizing an objective function over a convex set. That was the thing. So now then later we come up with a standard form because it makes our life easy. Okay, many solvers are expecting that form, and in our further course of analyzing inequality, analyzing the feasibility region, it will be easy if you stick to that standard form. Okay, so standard form is like a form that we adopt uh, to make our life easy. We can say that. Okay, but yeah, so in that form that we adopt, this is not convex. I agree. But what I'm saying is, then you should not quit. Okay, although when you see that this is not convex with the respect to standard form, you should not quit. Then you have to think, okay, although this is not a convex function, what is the set indicating by this inequality? It is the entire real line here. So that is actually a convex function. Okay, it's like you made a rule. You have some original rule. Okay, then you come up with a second rule to make your life easy, but it has some loopholes. You can roughly say that. Okay,
Like we have to follow
yeah, so most of the time it will work, but sometimes you can come up with an equivalent form. Okay, so then what you are doing in your problem is you are just dropping this. Okay, and now what you are getting is, for example, your function was f0x minimize f0x subject to minus x square minus 5 less than 0. Okay, so this looks like non-convex. Okay, so what I'm saying is, okay, I agree, this, let's say this is non-convex. Okay, I can come up with an equivalent problem which is just minimize f0x. Okay, I can drop this because that will be satisfied for all x. So now this problem will give the same solution as the first problem. Okay, this is equivalent problem. So although this looks like a non-convex problem, we can get an equivalent convex problem. So my point is, this is a final point. If you see something like this, you should not quit. Still you have the hope. Okay, is it clear? Okay, now onwards, we don't strictly think like this. Is just since we introduced the standard form and abstract form, I'm going into detail. But now onwards, in your daily life of research, if you have something, just if you have a constraint, just see it as whether you can come up with a convex alternative. Okay, an equivalent form. If that, just go with that. You don't need to worry about, okay, whether this is convex with respect to my standard form or abstract form. Forget about that. You have an inequality or equality constraint. Can I get a convex version of that? If that is there, you can go with that. But why we are introducing this kind of rule? Because it makes our life easy at many places. Okay, so keep that in mind. Okay, So let's go ahead. Yeah. We saw what is a quasi-convex function, right? And a quasi-convex optimization last time. It's the same. It is very similar to a convex optimization. All the rules apply here. Only thing is F0 is now, it's not convex. Now it is quasi-convex. Okay, of course, convex is also a convex is also a subset of this, right? So in general, if F0 is a quasi-convex function, we can say that this is a quasi-convex optimization problem. So the problem here is how this is different from a convex optimization problem is quasi-convex function can have uh, local minimas which are not global minimas. So here you can see that this point is a global minima. Here you have a local minima which is not your local global minima. Okay, why this is a local minima? Why are you saying this is a local minima? Because it comes from our definition of local minima. How do we define? To check whether a point is local minima, check a small range, a neighborhood. You should be able to find a neighborhood where this function has a value. This is the lesser or equal. In this case, this is equal value. So all the neighborhood has equal value compared to that point, right? So then that's a local minima. Yeah, so this is a problem here. Since all the local minimas are not global minima, that makes some issues, right? That's a huge issue, right? What was the beauty of our convex optimization problem? You do something and you somehow you found that one point is local minimum. Then you can confidently say that that point is a global minimum. But that's not the case here. That's the problem. So now let's see how to handle this. So that one way of handling this is convex representation of sublevel set of F0. So F0 is our now the quasi-convex function. So what we are doing is, so yeah, so let's consider the function. So this is a quasi-convex function F0x, okay? And so what we are doing is, okay, what is the sublevel set of this function? For example, t sublevel set is this set, right? This part of the real line, that is sublevel. So what I will do is I will I will use another convex function which through which I will represent this sublevel set. Okay, so here what I'm doing is to represent this sublevel set, I consider another convex function phi tx. Okay, and what will be the zeroth sublevel set of phi tx? Zero sublevel set is the values of x for which the function, the green function takes. So you draw a line here. So then the green function should take the value lesser than that one. Here it's a 0. The value is 0. So all these points, right? So what is the set corresponding to that? It is the same guy. Okay. So what I'm doing is corresponding to tth sublevel set of our original quasi-convex function, the red function here, we are constructing a new convex function, the green function here, whose zeroth sublevel set. So this is, remember, see, this is indexed by phi t. This is indexed by t. Okay. So corresponding to t, I have phi tx. So it is zeroth sublevel set of phi tx will be the same as tth sublevel set of this guy. So we can write that f0x is less than or equal to implies phi tx is less than or equal to 0. Okay. Now if I change t, I am coming up with a new sublevel set. Yes. Okay. Yes. Now I have a new function pi sx, which is having this, which is this, and that have a 0 sublevel set of this. Okay. Yeah. So if I can find a convex function like this, okay, you have an original quasi-convex function, but corresponding to each teeth sublevel set, I can find a family. This is family of convex function. Then we can use some trick to minimize the original function. That's the point. Yeah. So again, one more thing here. If you take two two values, t and s, here t is higher than s, then this function, what can you observe from here? This function for a particular x, for example, here x0, phi s x0 is greater than phi t x0. Okay. So in other words, if t is greater than s, phi tx will be less than phi sx here. Okay. So here phi t is decreasing or non-increasing in t. Okay. Anyway, so the point here is both sublevel set are 0. This is the teeth sublevel set of the original convex section phi 0x. Now this is the 0th sublevel set of the newly constructed convex function. So when t varies, this t vary. So this is a family of convex function. Now, if you have this, how can it how we can utilize this information? So let's see how we can solve a quasi-convex optimization with this. So yeah, so this is this is the original quasi-convex optimization problem, where everything is nice apart from this function, which is a quasi-convex. Now what I do is I will construct another optimization problem, which is a convex feasibility problem using this is the problem. Find, so be careful, this is not minimized. Find x such that, or subject to, phi tx is less than 0, then everything is safe. Okay. Now what happens is, I have this feasibility function, and I will check the feasibility for a particular t. I start with a particular t. Okay, and check the feasibility of this. So for a particular t, I will have a particular convex function. Okay, when you change t, when you increase t, you will get a different convex function. So this particular t, I will run this convex feasibility problem, which is a very easy problem, right? Find x subject to convex constraints. And if you find that x is feasible for that particular t, what does that mean? That means this is satisfied. Phi tx is less than or equal to 0. It is feasible, right? So that will be satisfied. What does this mean? If this is less than 0, so how do we construct a function? If this is less than 0, my f0 xt original function will be less than t. So you can say that this is less than t. Now, if this is less than t, the function at the value of x is less than t. What does that mean? That means t, this is not the minimum. Okay, t will be, this value t is greater than our optimal value, because the function can take values lesser than t. So it's not the optimal value. So that will be t. Okay. And if x is not feasible, then everything will be reversed, and we will come up at a final point where t is less than or equal to p star. Okay.
So if x is not feasible, no need to go for further. That you can continue.
Yeah, yeah. It's the same case with x is feasible also.
Yeah.
This step I wrote for you to understand. Okay. X is feasible, t is greater than p0. X is not feasible, t is less than p0. Remember, you can ask a question. Okay, x is not feasible, then the non-feasibility can come from this inequality, right? See, I wrote x is not feasible implies this is violated. This inequality is this violated, but this can come from this, right? But the point here is we are considering x from the feasible region. Okay, it will be clear soon. So the point is, so based on this, so now what we do is we check this for different values of t, and then you can you can get an idea whether t is less than or equal to optimum, greater than or equal to optimum value, or less than or equal to optimum value. So this is very helpful. Why? Because, for example, you have a function. Let's take a case in R. So you have a function whose minimum value is p star. Okay. Now what you do is you take two values of x. So yeah, I made a mistake. This is not p star. This is the value at which this is achieved. So let's say this is the point, optimal point. This is the optimal point. Or yeah. So let's start from this. So what I do is I will start my algorithm. So if you have this information, you can now easily design a bisection method. I hope you have studied this in your maybe high schools, right? So what does that mean? So let's say this is the point where the minimum is achieved. So I start with some numbers from some boundary points or some value, some points L and U. I pick up 2 points L and U such that it is lying on both sides of this. So if you run this algorithm with the t equal to U, if that gives negative value, then this will give positive value and vice versa. Okay. Now what I do is, so first I select this. When I start my algorithm, I go to the midpoint, L plus U by 2. This I will take as my initial t and run the algorithm. So if you run the algorithm, if this is feasible, convex feasible problem, that means t is greater than or equal to p. So in this case, t is greater than or equal to p. Okay. And okay, so yeah, I think again this was phase star itself. Yeah, not talking about it, because here we are considering the values of the function. Yeah, sorry. Yeah, so now we saw that at this t, we got t is greater than or equal to p because it's to the right of this, right? Now what I do is I replace u with this point and run the algorithm again. So now we will run the algorithm means we go to the midpoint and fix that as t and check whether t is greater than or equal to 0. So this is the basic bisection method. So if you continue this, at the end, you will be very close to this and you can reach very close to the optimum value. Okay, so maybe you can, so this is the algorithm here. Sorry. So the bisection algorithm here, where you start with L and U values, take the midpoint, solve the convex feasibility problem, and if it's feasible, then you take U equal to t. Else, if for example p was here, then you have to bring your L to this point and continue the algorithm in this interval. Okay. So this is repeated until what point? U minus L is less than an epsilon. Epsilon is like a value that we determine how much accuracy that we want. So finally, we will reach an epsilon neighborhood of this point. Okay, epsilon close. We are close to the optimal value by a point epsilon. We can decide that if you make epsilon very small, we need more iteration to solve this, right? So what is what is the length of the interval initially? U minus L, right? This was the length of the interval. Now after one iteration, we will make it half. So U minus L by 2. Next iteration again half. So at kth iteration, it will be U minus L by 2 raised to k. Okay. So now what we are doing, what we want to seek is that this interval has to be less than epsilon at kth interval. So this interval has to be less than epsilon. This is the input that we are feeding to the algorithm. So rearrange this, and then we can find that k should be greater than or equal to this quantity. That's what it is written here. So that means if you choose a particular epsilon, we can find based on u and L values, that is also input to the algorithm. You can find how many iteration you want to reach this accuracy of epsilon. Okay, so this is the bisection method. So if you have a convex problem, quasi-convex problem, you can use this bisection method to solve it. Yeah, so you may wonder how can we, so one point it is not clear is how can you construct this convex family of convex function, right? So here is an example. So you have a function here, f0x equal to p by q, okay, with p convex and q concave, and p has to be greater than or equal to 0 and q is strictly positive. So in this case, if you define the function like this, this will be a quasi-convex function. Why? Why this is a quasi-convex function? How do you examine the quasi-convexity? You will see whether this set x such that px by qx is less than or equal to t, right? This is the t sublevel set, whether this is a convex set or not. That is how you prove the quasi-convexity, right? The alpha sublevel set or t sublevel set has to be convex. So is this happening here? So I can write this as, so this part I'm writing as px minus tqx less than or equal to 0, right? So this is what? This is a convex function. What will be this? This is concave. Q is concave. Then what will be minus Q? Convex. T into minus Q. It depends on whether T is positive or not, right? But we have the assumption here that P and Q has to be greater than or equal to 0. So this will be positive. T. When you consider this, T has to be positive. So this is positive. So what I'm saying is, in altogether, you can say that the second function is convex. So you are adding two convex functions, which will be convex. So we proved that this function f0x is a quasi-convex function. Now what we are doing is we are constructing a family of convex function for this to solve the bisection method. So here, a very simple way to do is construct phi tx such that px minus tqx, it is equal to phi t is equal to px minus tqx. Okay, so this is again, it satisfies all our constraint, all our criteria. If phi x, if p by q is less than t, which implies phi t is less than 0, right? If that's what we saw here. If p by t is less than t, then this is the phi t, right? This is our phi t. This will be less than or equal to 0. So that is satisfy our constraint. Again, this is a convex function that we already proved. Okay, so we have a family of convex functions. So when you have a quasi-convex optimization, so easiest way to solve, a straightforward way to solve is try to find a convex function which mimic its sublevel set. And then if you have that, you can use this bisection method. Okay, so let's move.
Like in the PDF,
Yes,
where is this stuff?
P star. P star is the optimal value of the original function. So where it will be this one. Yeah. Now we will move to more interesting section. So now, so far we were seeing how can we define a convex problem, and we also saw how to solve how to link a quasi-convex to a convex problem. Okay. We also saw some optimality condition. Okay. With this in mind, and especially with our standard form in mind, now we are moving to get used to the standard classes in optimization problem. There are family of problem or classes of problem. For example, we start with LP. This is a simple class of problem. Now later we will see quadratic programming, QP, QCQP, SOCP, STP. There are many families of problem. So why we are learning is, for example, if you have a problem and you bring that to this problem, this form, okay, or any, let's say you know what is an SOCP class of optimization problem. Then in your research, you formulated a problem and you saw that it is an SOCP framework. Then this class is very well studied and you can readily use the solvers for that. Okay, you don't need to worry about it. If you have an SOCP or STP or LP, you don't need to worry. You know that it can be very easily solved. Okay, so that's why we are getting familiar with this standard form to make sure that if you have that problem, you don't need to quit. You can be very happy. So we will start with the very simple class. This is the very old optimization framework, which is a linear programming. So what is a linear programming? So you can see that all these are with respect to our standard form. Okay. So linear programming is that now the objective function, we had f0x. Now the objective function is an affine objective function. Okay. And what about the constraints? Constraint is also, so the equality has to be affine. Okay. This has to be a linear equality. There is no doubt in that. If you replace that with a nonlinear inequality, then that moment is not convex. Okay. But here initially we had Fix less than, what was it? Some Vi or something. I don't remember which notation we followed. Yeah, it was 0. Okay. So there is no problem if you write like it, because you can always bring Bi to the left side and define a new Fix. Okay. So this was our initial, our standard form. Now what I'm saying is this Fi also has to be linear or affine. Okay. So that's what you are seeing here. Affine objective function, affine inequality, and equality is also affine or linear. Okay. So it's a convex problem with affine objective and constraint functions, right? All the constraints function are affine. Now, if you see this, what is the set formed by these constraints? Means inequalities and equalities. What will be that? It will be a polyhedron, because I hope you are okay with this notation. G is a matrix, so that means this will have, for example, G is like G11, G12, G13, like the G21, G22. Okay, what you are doing is you are multiplying that with X. So you have X1, X2, X3, okay? So corresponding to each row, you will have a inequality here, okay? So that means G11, G12, G1, or if I denote this row, first row as vector G1, so this will be G1, vector G1 transpose X, vector X, and now we are saying that that is less than H, so less than H1, first element of this, okay? So like that, we have different rows. Each rows of the matrix are the gives you the coefficient corresponding to each inequality. So how many rows are there? 3 rows. So you will have 3 different inequalities inside this. Okay. Yeah. So now we have three inequalities, right? Affine inequalities. So that means you will have three half spaces, right? So let's say that we have here 1, 2, 6, right? 6 inequalities. That means your matrix G has a 6 number of rows. Then what will be the joint constraint? That will be intersection of all half spaces. Then you will have a polyhedron. If you put an additional constraint, equality constraint, then a line will pass through this. Then the feasible set will be this point. That is also a polyhedron. That's also a polyhedron. We especially, so I especially mentioned this when we saw a polyhedron. Line segment, everything can be visualized as a polyhedron. Okay. Yes. Hyperplane. Yeah. So what you can see is yeah. So let me see. Yeah. So this is the polyhedra. So in this case, I'm not taking any equality constraint. So I have this. So now what I'm saying is now my optimization, the solver will search in this region. Okay. And let's take the level curves of our objective function like this. So it will decrease to this direction. Okay. So why we are taking a straight level curves? Before we were constructing level curves like this, but now we are taking level curves like this. Why it is like that? Because what is the level curve? It's the contour of the objective function, right? What is our objective function here? It is an affine function, right?
Yeah.
So that will be, for example, in a 3D, it will be a plane, right? So this is the plane. So that level curve will be straight lines like this. So then what you can see is, so now you are finding a point, trying to pick a point to this direction because objective function is decreasing to that direction, but it has to be within this polyhedra. So that will pick this point. Okay, so you can see that always in linear programming, the optimal point will be that will be at the vertex, the corner points. Okay, so we will take a small break here. This is clear? Any doubt we can?
Yoshin,
Yes.
can I ask about this? So this polyhedron, I still don't entirely see it. So this Gx is smaller than h.
Yes.
This G is 6 times 2 in dimension because it is a surface, just x1, x2, and it has 6 sides, as you say.
Now what I'm saying is, in this case, G should have 6 rows.
At least, or yeah.
No, the thing is, each row of G corresponding to one half space.
Yeah.
So this is the equation or inequality corresponding to first row. So I am denoting the first row vector here, this vector, as G1. Okay.
Yeah, but this I understand. But this it still means you sort of have to be lucky that it forms a polyhedron, dependent on the on the values in your G matrix.
Yeah. So your question is, for example, if you have this, okay,
Yeah.
and this is whether this is not forming a polyhedron, right? That is your question.
I was wondering what does the AX is B do? I like
Okay.
so one thing is the GX is smaller than H.
Yeah.
I can imagine, okay, this could be a polyhedron, but then you put it on both, also AX is B.
So that's the point. When you hear the word polyhedron, of course the figure that is coming to our mind is this, okay? But there are other polyhedron also. For example, this is a polyhedron, just a line segment. That is also defined as a polyhedron because that is the intersection of two half spaces. One is above this, you are saying one is below this, and when you take the intersection, you will get this, okay? So the intersection can be in any form. In this case, you have a nice intersection, and you are getting this guy here. But it can be a, like, that's why maybe we will go back to the lecture where we introduce polyhedron. Yeah. So that's why I wrote here a hyperplane, line, ray, line segment. These are also polyhedron. So they can be visualized as a like solutions of finitely many linear and linear inequalities and equalities. So this is how the polyhedron is defined. Okay. So you have many sides here, many half spaces corresponding to each equation. Then you take the intersection here. But what happens if you take this inequality here? Then you will get a line here. And then when you take intersection, you will be only getting this point, this line segment. Okay. That is also a polyhedron, just a line segment.
Yeah, and because you already have this internal surface of the polyhedron, this line doesn't add anything, really.
No, you have this internal surface of.
Yeah,
surface,
so this
okay.
line, this if you add a line, that
will
then it
just
doesn't
when you take
change
intersection,
anything.
it will just that. So line is like this, okay.
Yeah.
When you take the intersection, it will just pick this segment, which is
yeah, because both have to be true. Yeah.
Yeah,
I see.
both has to be true. So,
okay, thank you.
So what my point is, this is how the polyhedron is defined. It need not be a nice shape. It need not be the polyhedron, the image of the polyhedron that is in our mind. Okay, it need not be in this. This is also a polyhedron, just a line, a ray, a line segment, even a hyperplane. So anything can be a polyhedron.
Yeah,
so
I see it.
Yeah. So that's why we have this here. So corresponding to each row of this, you will get a half space, okay, and many half space. That means in this case, we have 6 rows here.
Yeah, at least 6 rows, I would say, because you, of course, need to be lucky that the row actually adds something. Yeah?
Yes, correct.
Yeah, okay.
Yeah, for example, one of the constraint is redundant. It was showing a half space this side like this, then that will not do anything to this. Yeah, correct. But the moment if you add this, then that can be like this. Then in that case, our polyhedron is this part. If this is like this, we don't have any feasible region because intersection is null set there.
Yeah, that's okay. I see it.
Yeah. Okay, fine. So we let's continue. Yeah, let's continue. We will see an example, a diet problem. This is a simple problem where. So now we are going to design a cheapest healthy diet. Okay, fine. So let's say you have n different food. For example, 1 apple, 2 orange, something like that. Okay, and now we are going to buy this from the supermarket, but we have a constraint here. First thing is, yeah, let's see the framework. So I am buying x1 quantity of apple x2 quantity of orange, like that xn quantity of food n. Okay, and the cost of a particular guy, jth food, for example, apple. Cost of apple is, let's give an index for apple 1. So C1, that is a cost. So cost for unit food. Okay, like for example 1 gram of that. And also that contain jth food contain a nutrient aij of I, an amount of nutrient aij corresponding to the nutrient I. For example, nutrient 1 I am taking as vitamin, nutrient 2 as protein, something like that. So that is this condition. Okay, now the requirement is again, yeah, healthy diet requirement. So I should have nutrient I, for example vitamin A, at least Bi. So there is some threshold. So from the diet, the vitamin that I'm getting should be greater than that threshold. That's the concept. So how do we make an optimization problem this? So we have the diet problem. First thing is, what are we going to minimize? The price, right? Overall cost. So this is the amount that we are purchasing. So this is the unit that we are purchasing. This is the cost for unit of each food. So then that will be this quantity C1 x1 plus C2. So that we can write as C transpose X. Okay. Now coming to the constraints, this nutrient constraint. So for nutrient 1 for this first index, for food 1, you are taking x1 amount. So for unit amount that has A11 amount of that particular nutrient, A12 like that. So this will give this inequality that has to be less than B1. For second nutrient, again less than B2 like that. Okay, so this you can write as in a matrix form. Ax is less than or equal to B, where B is this vector, A is all these A coefficients, and X is the vector X. Okay. So now simply our optimization problem will be C transpose X subject to Ax greater than B. Of course, X has to be positive. So you are buying a positive quantity amount, right? It cannot be negative.
But how it will be clear?
That means you are determining, for example, apple. From apple you are getting a particular vitamin. Let's just assume that apple from apple you are getting only vitamin A. Okay, I don't know about this.
But X is the quantity, right?
Yeah, it can be 0. That means you are not buying that guy.
Not buying.
But the nutrient in that specific food is obtained from other food. That's what that. For example, you are buying orange. It has vitamin C, but orange is very expensive. But the vitamin C can be obtained from other food that you are purchasing. So if it's very expensive, maybe the optimization problem will discard that. The overall cost has to be minimized, right? So that can be 0, but it cannot be negative, which doesn't make any sense. So this is a case of linear programming. So we are here. We are discussing the very simple class of convex optimization, which is linear programming. So yeah, this is a simple example. Another example is piecewise linear minimization. So what is piecewise linear function? We already saw. For example, a absolute value function is a piecewise linear function, which says that take the maximum between these two lines. Okay, let's see here. So what is a piecewise linear function? It is defined by this form. It is defined as this, where you are taking maximum of different affine functions. Okay, so here you have m different affine function. So for example, this is one affine function corresponding to a1 x1 plus b1 equal to c. Another one is this one, and this one. You have different affine functions. Now what you are doing is you are taking the point-wise maximum. So what is the maximum of all this? So each point, for example, if you take a point here, you will see what is the maximum. So that will be this guy. Okay, so if you take the overall maximum at each point, you get this convex function. Okay, so now what this optimization problem is asking you to minimize this piecewise linear inequality. So we already saw that. Yeah. No, you don't need to go for bisection here. Bisection is used when quasi-convex problem, because it was difficult to solve. Then we were trying some way to solve it. Okay, here this is a nice convex function. You can easily solve. What is the problem with the straight line? This is a convex function. Okay, so this we will show that this is a very simple case of LP. Okay, so yeah, so now I want to minimize this. So this is that graph that I'm showing. I want to minimize this. So this I can write. This we already saw in previous class, epigraph method. So instead of finding the minimum of this, now I am doing an epigraph approach where take a t, okay, and then do the minimization over x and t. So now what you are doing is take t and find like try to reduce t and find the minimum value of t, but then if t has to be greater than or equal to f0x. So at this point, if you go further from this point, then t will decrease. T will be less than or equal to the function, original function here. So by doing this, what you will be getting is this point x opt t opt. From this, you can pick the x opt. So that is what this form. So in order to minimize, in order to perform this optimization form, this is not linear, right? This is not a linear optimization form, because if this was not there, then it is linear. But now you are asking, what you are asking is to take the maximum. Then the overall function is not linear. So for example, if you take absolute value function, this is not a linear function. Okay. So now this was non-linear, but still now you can use this epigraph method and form a very nice linear programming where the objective function is constant, and this is also inequality is also given by affine function. So now that's why I said you don't even need to think about any bisection or something here, because this is a nice LP which you can solve very easily. Okay, this is the simplest form of optimization. Yes, so that is piecewise linear minimization. Again, this is not applicable for any piecewise linear function. It's applicable for a particular function formed by this form. For example, you can construct a piecewise linear function like this. In this case, this is not convex, right? This is linear, 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 and again linear. This is piecewise linear function. This is not convex. So you cannot do this for any piecewise linear function. You can do it only for this function, this kind of function, where the resulting function will be convex. No, why this is a convex function? So why do you this one? No, you cannot do, because this is not quasi-convex. Quasi-convex optimization can be done only for quasi-convex functions. Okay. Because if you take alpha, how do you define alpha sublevel set? How do you define a quasi-convex function? You have to take, for example, this is the domain. You have to take alpha sublevel set that has to be convex. So if you consider my alpha to be here, the sublevel set will be this part and this part, right? This is not a convex set. So to find a function is quasi-convex or not, it is easy. One thing is you can check the sublevel set, or other thing is, this is very informal way I'm saying. It looks something similar to a convex function, right? Okay, but there can be a function like this. Okay, I'll draw here. Yeah, there can be a function like this. This is also quasi-convex. Okay. So in other way, you can think that, okay, this is a ground. You have a ball here. You are just kicking the ball. And finally, the ball should reach here. At this point, if you keep on kicking, it will go and the ball will reach here, right? So that will be the global minimum. Okay, I think, is it a correct way of explaining? No, sorry, forget about it. So here is this. Yeah, that is also, we can say that, but yeah, the thing is, so if you like move this ball and it reaches a point where if you further you, it will come back, right? But what happens if it's a non-convex function? You can find many such places where this is happening. This is happening at local minima, right? But quasi-convex function, there can be other local minimas, but they will be like a straight form, right? So then that place, if you keep kicking ball, it will move forward, and finally you will reach this dip. Okay. Anyway, this is very informal, just a funny. I don't know whether there is a loophole in that, but I think it's correct. Yeah. Yeah. So let's move on. Yeah. So another example of LP, Chebyshev center of a polyhedron. So what is this? We have a polyhedron here, and now this is the center of Chebyshev center of a polyhedron is the center of largest ball inscribed in the. So just to consider a ball, a largest ball that can fit into this, and then the center will be Chebyshev center. Okay. So how do you find this center? That's the question. Or what is the maximum radius of this ball? So now we already saw that a ball can be represented in this form, xc plus u, in the first class. So we also saw another formula, x minus xc, I think less than or equal to this norm square less than or equal to r square or something. Okay. So this is another way of representing this, xc plus u. That means you have a center xc. From there you are picking point xc plus u. That has to be, and the u is deciding how much farther from x, and that has to be less than r. So you cannot go beyond r. That is this meaning. Now, what I want to do is, so here we have a polyhedra. So this point has to be the pole. So how can we say this? Just a second. Yeah. So all the points inside this ball has to be in the polyhedra, right? So we are looking for a like a large size, maximum size ball within the polyhedra. That means it cannot be like this. The points cannot go outside polyhedra. Okay. So all the points within the ball has to be in polyhedra. So how can we write that? We write this. So then we have to make sure that the points that we are picking has to satisfy this inequality. Okay. So what is our point? Xc plus u. So just substitute that here, A transpose Xc plus u, and u less than r. This means that these points are inside the ball. And then take the maximum of such point, maximum value of that, okay, that thing. So you have the points like this and take the maximum of that. That has to be less than BA. If you are saying maximum is less than BA, then all other values less than this maximum will all, of course, will be less than BA. So now how do we evaluate the supremum? So you are going to find the supremum, A transpose XE plus U. So that will be A transpose XE plus A transpose U. So here the variable is U. You are changing U to find different variables. So XE is fixed, okay? You are changing U. How do you get this? So now only thing is this time, which is playing a role in your maximization, okay? So what is the maximum of this? So by when I say maximum here, it's supremum, okay? Both are different, but loosely we can say it, right? So so supremum of A transpose U, this is what we are going to find. So this will be, what is A transpose U? It will be norm of A, norm of U into the angle between that, right? So the maximum will be when theta will be equal to 0. That is, U is parallel to A, and U will take its maximum value R. Okay, so this term will take the supremum value of R into U square. So this is the maximum. So now what you do is, so this is a criteria for the points of ball to be inside the polyhedron. Now what you do is find the maximum R which satisfy this criteria. Okay. So again, you can see that this is a linear programming, because the objective function is just R, like it's an affine, right? And this is this inequality affine. You can see the norm 2. So the thing is, when you are asked to examine whether this inequality is affine or not, first thing is, you should not be scared by this norm. Okay, first thing is, what is the optimization variable here? It is R. Okay, so now you just focus on this R. Is this affine as a function of R? That's the question. So then, if R is a variable here, this is a constant, these are constant. Okay, so then this is readily affine, right? XC is also constant. XC, yeah. Yeah, so some example, yeah, these are some examples. Now we will move to linear fraction program. This is not a different class, but this is something similar. This is a function which can be, this is a problem, convex problem, which can be reduced to a linear program. So let's see what it is. It is a problem of the same standard of LP. Okay, this is LP, right? No, this is not LP. You cannot say that this is LP. You can say this is LP when f0x is a affine function. So now this is a linear fraction program when f0 is given by a linear fractional function that we already saw. What is a linear fractional function? Okay, that is a function of this form where this guy has to be positive. The denominator has to be positive. This we already saw. Now, how can we solve this? So we already saw that this is a quasi-convex function. This we already saw in the class. So you can consider the sublevel set of this, and find what is the sublevel set. I think this is both quasi-convex and quasi-linear. This is quasi-linear, right? Let me just check. Yes. Oh, it's long back. Oh, it was in previous lecture. Anyway, it is quasi-linear actually. Okay. You can check it later. Yeah. So this is a quasi-convex also, right? So in this case, how can we solve this? So you are given a quasi-convex optimization problem. So one way to solve is, you already know, bisection. We can go for that. Another way, for this special function, okay, remember, not for all quasi-convex function, only for this special function of linear fraction. You can use a trick here. You can bring that to an LP form, where you make a simple substitution. So this was your original problem, where you minimize this strange function with respect to inequalities and equality constraints. Now what you do is you make a substitution. You introduce a variable y, a vector y. So y is this part, x by e transpose x plus f. Now another variable z, that is this part, 1 over e transpose x plus f. Okay. Now, so remember, this is, okay, sorry, this is a scalar. Oh. This is a scalar, right? Yeah. This is a vector. Okay. Yeah. So z is a scalar. Now, from this, what can you conclude? If you consider y, vector y by z, it will be x, right? Because this term will get cancelled, and it will be x. Now we are going to rewrite the original problem in terms of x, y, and z. So what was our f0 objective function? It was this guy, right? And now I can rewrite that in terms of y and z like this. C transpose y, that means y is this. When you take C transpose y, it will be C transpose x, okay? That will be this term, right? Plus dz. So it will be dz is this, that is this guy. Yeah. So
It's also the vector issue there. Huh? The dz, the d is not the vector.
Yes, correct. Thank you. Yeah. Okay. So
just assume that D is not
sorry.
that location you have put everywhere. So that
it is there everywhere. No. Only one place, right?
There also is not x equal to.
Okay.
And then you are solving with blue pen, so it's better.
Yes. Anyway, if at some place I am, D is a scalar, okay? Even if at some place I am making mistake, please consider that D is a scalar. Yeah. So yeah, objective function I can write like this. Now we take the first inequality, gx less than or equal to s. Just substitute for x this guy, yeah. So you will get this, and now you got a new inequality. Similarly, for x equal to b, you get a new inequality. Now I can use this objective function and these inequalities and equalities, but only problem is here now the new optimization will be in terms of y and z. So we didn't take y and z. We made a specific choice for y and z. Okay, so there will be some constraint which is coming from that specific choice. One is z is 1 plus e transpose f. In our original function, this is positive. That is how we defined linear fraction function. That means this is positive. That means z has to be greater than 0. So that constraint will come. Another thing is y and z has a special form, so that if you consider this guy, E transpose Y plus F of Z, you can evaluate this. So E transpose into Y, this is Y, plus F of Z, this is Z, that will be 1. Okay. So these two constraints also has to be part of the optimization problem. This is coming because we made this special choice of Y and Z. So now pick all these things and form a new optimization problem. Now this is in Y and Z. This is, we are minimizing this in Y and Z. Okay. So find this, and at the end you can find X. Okay. So what is this now? The interesting thing is this is an LP. Everything is in the form that we want. This is an LP. Yeah. So this will give X. So sometimes we discuss, sometimes we say about the argument value, the optimum value, sometimes the optimum point. Okay. But both are okay, because if you have one, if you have optimum point, you can substitute that in the function and get the optimum value. You got what I'm saying, right? So you have a function here. Sometimes we talk about optimum point, but if you get this point, you can get this value, right, easily. Yeah, so we will skip this slide. Let's move on. Let's move on to the, let me just check whether we missed something. Yeah, so yeah, that's it. So what we just saw is that a special class of quasi-convex problem, which is a linear fraction program, can be solved using a simple LP. Now let's move to the next topic, that is quadratic programming. So we saw LP. Now we are moving to a new class, which is QP, more complicated class. LP was the simplest form. This is some more complicated. Why this is more complicated? Because here, so in LP, we were just having this affine term. Now we are adding a quadratic term here, x transpose p into x. Okay, everything else is same, right? So now this is called quadratic programming. So what you are doing here is, again, the constraint sets here, the feasible region is polyhedron here, because we have the same affine inequality and affine equality, right? Which will give you a polyhedron. Okay, that is same. Okay, feasible region is same as LP, but only the difference is, earlier this was an affine function where we have straight level curve. Here we have a quadratic function, so which will have level curves like this. Got it? Right? Now, but one condition, you cannot say that you cannot solve this for all choice of P. For this to be convex, what should be the condition of P? That has to be positive semi-definite. This we already saw. How do you say that? How do you check the convexity of this? Differentiate twice. The matrix that you are getting has to be positive semi-definite, right? So when you differentiate twice of this function, you will get P. Okay, that has to be positive semi-definite. Then only this objective function is convex. Then only you can solve this. So yeah, so quadratic programming is minimizing a quadratic function over a polyhedron. So now what we can see is that the LP, which we just studied, is a special class inside QP. Why you are saying special class? Can you construct an LP from this? It's easy, right? Just make this term 0. Okay, or just put P as 0 something. Yeah. So that then all LP is a subclass of QP. QP is more general than LP, right? So examples. One is this we already saw, the least square, okay, which will have a solution of the form A dagger B. A is the pseudo inverse, which this we already saw, right, in the first class, A transpose A inverse into A transpose. So this is the least square, which has an analytic solution. So this is a quadratic programming with no constraints, unconstrained quadratic programming. This least square, okay. But of course, you can add constraints. You can say something like x has to be less than u or greater than L. You can call it as constrained least square. That's it. Okay. So yeah, so you can add, but this will be QP, only least square will be QP, constraint least square will be QP, only when the constraint that you are adding should be of this form. Okay. Yeah. Now let's see another example. Linear LP with a random cost. So you have a linear program where the cost is objective function is random. In that case, this is not a simple linear program. This is not even a linear program. That is, it depends how you solve it, but you can show that one way of formulating it leads to a quadratic program. Okay, let's see what it is. So here, let's say you want to minimize this. You have an objective function where you want to minimize C transpose X. Okay. Now what you are saying is C is not deterministic. C is a random vector. Okay, with mean C bar and its covariance sigma. Okay, in that case, how do you minimize this? Okay, one way to minimize this is a very straight way is this. What you do is you just take minimum of expected value of C. Okay, you take that and then transpose X and everything is same. Okay, so in this case this is an LP, right? You just instead of C you are just finding the mean and just substituting there. So that's an LP. But this may not be the best way to do this. Here we are not considering the variance. So what you are doing here is you are trying to minimize something. So you have a variable something like this, and this is the mean. Okay, you are trying to minimize by substituting the mean. Okay, mean of the variable in the convex. This is our C bar, expectation of C. Okay, this is what we are just substituting, but at the same time there is a constant here. What is the variance of the distribution? If the variance is too large, then this will add more error, right? There can be like it can be on either side to any extent if the variance is large. So then one clever way of doing this is, okay, I do this, I substitute this, at the same time I add I also minimize the variance of this. Okay, so bring that variance part also into objective function and minimize that. So that's what we are doing here. So here expected value of C, okay, this is the simplest form, plus gamma times variance of C transpose X. Okay, this is expected value of C transpose X. X is a constant here because the random variable, I mean constant, I mean it's deterministic. It will not affect the expectation. Yeah, so then variance of C transpose X. So what will be the variance of C transpose X? You can find this, you can read this. This is very simple, like your from bachelor's. Then that will be X transpose sigma X. So now you can rewrite the form as this. Okay, and so, the inequality constraints will be same, right? So then what is this? Is it a QP or LP?
Quadratic?
Yeah, this is a quadratic, right? How this is LP? Because you have, see this term,
Yeah.
X transpose sigma X. So the optimization variable is X, okay?
Yeah.
Okay. The randomness was in C. That's what we said, okay? So this is quadratic in X because you have this X transpose sigma X. So this is a quadratic code. So what we just saw was a linear program with a random cost. When the cost is random, when cost is this guy C. For example, in our diet problem, we can say that there C was the prices, right? Okay, the price is not fixed. We are going to purchase it on like 5 days later. I don't know the exact price, but I know a chance that, or a mean value and how much it can vary. That's the question. So we are modifying our diet problem, original diet problem, which was having a fixed cost. Now we are making a random cost. Okay, we are adding randomness to the cost. In that case, one better way of solving this is to add variance. But when you add variance to the objective function, you will get a, now our LP is not titled LP, it's a quadratic program. Okay. Yeah. So one interesting thing is this guy gamma. This is the hyperparameter here, which keeps the trade-off between this and this. If you keep gamma to be too large, then the optimization problem will give importance to this part. Okay, it will give higher priority to minimize the variance. But if you, for example, if you put gamma equal to 0, then it will discard. If you keep gamma to be a low value, then this will be given higher importance in the optimization problem. So like that, this is called a hyperparameter in machine learning. So usual way is to do you can tune to get a good hyperparameter to get a good result. Okay. Yeah. So that's the conventional way of doing this, but there are people doing researches on that. I think Kevin is trying to do that. Yeah. Now, yes, we have 2 more minutes. Yeah, so let's move to, so we saw what is LP, what is QP. Let's move to the next class, which is quadratically constrained quadratic program. So it is the same guy. We have a quadratic objective function. Now only difference is earlier we were having an affine function here, but here also we are adding quadratic constraints. Okay, so it's very simple. It is a QP with quadratic constraints. Okay. So I equal to 1 to m means you can have m different quadratic constraints. Yeah. Again, this has to be positive semi-definite. Otherwise, our assumption of convexity will be violated. So what you can see here, how do you visualize this? Here, you are minimizing a quadratic function. Okay, maybe let's draw the level curves. You'll be having level curves like this because it's a quadratic function, right? And now what is the feasible region? For corresponding to each inequality, so this is a quadratic inequality, which gives you an ellipse, right? This we already saw in the first class. So corresponding to each P, for example, if you take consider a particular P1, you will get an ellipse whose length of the axis will be determined by the eigenvalues of the ellipse. It will be root lambda 1, lambda 2, something like that. So corresponding to each I here, or each Pi, here I'm considering three quadratic constraints. So we'll have 3 ellipses, okay? And then it should be satisfied for all the ellipse, or all the region. So that will be the intersection here, okay? This is the region from the quadratic constraint. We also have an affine constraint that will be a line through this. So the resulting feasible region will be here, just this part. No, that's not as affine function, right? This together makes a quadratic function, which gives you the ellipse. No. It has other part also. Okay. So it's like what's the equation of a circle? Let's take a simple circle. For example, x minus 2 is let's consider a disk. Okay, x minus 2 is less than or equal to r square or pi square 25. Okay, that's a disk, right? When you take square the x minus 2 whole square, you will get a 10 2x, right? Minus 2x. That is the stem. Otherwise, that has to be in origin in our case. The center has to be in origin. Yeah, so this is what is happening in QCQP. So again, we can say that that is more general class of QP. Why? Because how do you get a QP from this? We just consider these matrices as 0. Okay, so then you will have an affine inequality that will be equivalent. So we start from a very simple class LP, more complicated. Okay, but you can say that LP is a special QCQP, a very simple form of QCQP. Okay. Now, I think it's better to stop here. Yeah, we'll continue on next class.
So,
yes,
but also QCQPs, or what's it called? Yeah, they have a solution. I mean, you can find the solution. It is
yes, of course.
a convex problem, and
so yeah. So let me make this clear.
So it,
yeah,
this hierarchy you depict there is just in terms of easy to hard, but not from possible to impossible or something.
It's not from possible to impossible. It's from easy to hard. But the interesting thing is, so all the classes that we are seeing here are standard forms of this hierarchy inside the convex problem. All these are very well studied. All can be very easily solved. Okay. The interesting thing is, for example, if you take a solver, a standard solver, which is let's consider CVX, which you are going to study soon. So if you take a CVX solver, so that is the architecture of CVX is built for the the general class. So we will see that that will be STP. It's the most general class. Okay, so that the CVX is designed to solve a STP problem. Okay, the architecture. So even if you plug in an LP, okay, it doesn't have a separate solver for LP. It will be solving STP only. Okay, but just making those terms 0.
But okay. It would be faster then, I guess. Yeah.
It will not make much difference.
Okay.
Yeah. I don't know in exact speed, but of course it will consider. It will not do blind STP. It will consider all the sparsity pattern, all the zeros. But I will say that there is no much difference in the speed. So and for example, and next we are going to study SOCP that can be almost solved as fast as just a linear program. That's what happened. Okay, so the conclusion is, if you have a problem to solve and the problem happened to be in any of this class of problem, or even up to STP, it can be solved very easily. That's the conclusion. There is no need to worry. It's readily solvable. Okay, that's it. Fine. So let's stop here.